diagonalization, here the goal is to be able to use what we know about eigenvalues and eigenvectors, and to apply that in this very neat application, and that is it possible to find or force a matrix in some kind of way, transpose it, change it into its diagonal representation. We can do that, and we talk about similar matrices. I wish I didn't put it here, but there's a list that says that if two matrices are similar, what are they talking about? And it just lists all of these cool patterns. Um, I just thought about it. um, if some of my students question me about it, I will post it for you in Blackboard. But if not, then we'll just move on, right? um, I have to find it myself, but it's really cool stuff. This notion of similar is a mathematical term. Here, two square matrices of the same size, A and B, are said to be similar if there exists an invertible matrix P such that B is equal to P inverse times A times P. The real cool thing about that is that it goes the other way as well, and that's what I have here. Um, if I can find my highlighter, I was about to use a real marker on my screen. Um, that if the matrices are similar, then likewise A is equal to P inverse times B times P. Matrices that satisfy this property are said to be invariant. So invariance in mathematics is the same concept as similarity. This matrix P inverse times A times P is then forced to be a diagonal matrix. Now, the real cool thing is that everything that you have talked about in the previous section is used here to the fullest. So there's nothing new here that we're learning except to be able to write this form as if you're given a matrix A, you can find a diagonal matrix B by juxtaposing here P inverse times A times P. And then the question is, what is P? And once we get that, then we're done. A square matrix, the definition of square matrix here is said to be diagonalizable if it is similar to some diagonal matrix. Well, we just talked about that. That is, if there exists an invertible matrix P such that P inverse times A times P is diagonal. In this case, P is set to diagonalize A. Here, diagonalizable equivalents. If A is an n by n matrix, the following are equivalent. A is diagonalizable, and then A has n linearly independent eigenvectors. Well, that's something that we talked about. This next theorem, if an n by n matrix has n distinct eigenvalues, then A is diagonalizable. That's pretty cool to know, I guess. Now remark, the matrix P consists of, and here's all you need, the matrix P is just that, is the matrix of the eigenvectors that you found back in the previous section, listed as columns. And then the matrix P inverse times A times P is a diagonal matrix, and what it looks like is it's a diagonal matrix, and the entries along the main diagonal are the eigenvalues. Pretty cool. Well, let's begin here. So what we want to do is to find the eigenvalues, and then from there find the eigenvector, and that will form that matrix P. So the determinant of lambda times the identity minus A is equal to lambda minus 2, this is 2, because of that negative here, right? -9, 0, lambda -3, 2, 0, 1, and then lambda -2. So I'm going to find the determinant by cofactor expansion along the first column, because there's only one term, because the other two terms are 0. So this is lambda -2, and then you remember we delete its row and column to find the matrix of the subdeterminant, or the determinant of the submatrix. So this is lambda -3 times lambda -2 -2. So then we solve, that's equal to 0. So we have lambda -2, and this is lambda squared minus 5 lambda plus 6 minus 2 is plus 4. And we could factor that again. So this is lambda -2. And because I'm left-handed, I write my lambdas backwards. I'm sorry. So this is lambda -4. I almost forgot factoring. I was about to say, what the? And lambda -1. So we get lambda equal to 2, lambda equal to 4, and then lambda is equal to 1. Okay. So here, let's let lambda equal to 2 to plug that into just the matrix. Plug that into the matrix of lambda -2, 2, -9, 0, lambda -3, 2, 0, 1, and then lambda -2. So we plug lambda equal to 2. Let's look at that on the, I guess I have space here. This is fine. I was going to turn the page. So we get 0, 2, -9, 0, -1, 2, 0, 1, and 0. Okay. Now we're going to put this in our calculator and reduce. So we're going to do reduce row echelon form. I'm going to go ahead and find the other two. So let lambda equal to 4. So in doing that, we have 4 minus 2. We get 2, 2, -9, 0, 1, 2, 0, 1, and then 2. And then let lambda equal to 1. So that gives us -1, 2, -9, 0, 1 minus 3 is -2, 2, 0, 1, and let's see, what is that? That's -1. Okay. So now for that lambda equal to 2, You remember we got 0, 2, -9, 0, -1, 2, 0, 1, and 0. So that's reduced on the calculator. And so in that reduction, we get 0, 0, 0, 1, 0, 0, 0, 1, 0. All right. So what that says is that x sub 2 is 0, x sub 3 is 0. So x sub 1 is the floating parameter. So x sub 1 is equal to t. So the eigenvector would be 1, 0, 0 times that t. Now I do the lambda equal to 4 in red. So we take lambda equal to 4, and you recall that we got the matrix 2, 0, 0, 2, 1, 1, -9, 2, and 2. And then so now on the graphing calculator, I'm looking here at 1, 0, 0, 0, 1, 0, -13/2, 2, and 0. Now it's interesting because the solutions that that's given uh, by Webb-Assign, these numbers here, which I got from Webb-Assign, it seems that he didn't use reduced row echelon form. It seems like his reduction was row echelon form. But I'm using something better. And so what that means is that my P was different from his. But the result, once you calculate even my P inverse times A times P, you still get this. Um, so apparently P is not unique, right? And so you can put my answer in the way I do it, and that's cool. And Webb-Assign is going to mark it right. So we don't have to be like him, right? You can be like yourself, and because you understand it, and you just do the work. All right. So, and let's see what color for maybe blue for this lambda. Oh, I forgot to get the eigenvector for lambda equal to 4. Good. So let's just get it here. Notice that you look on the main diagonal, and there's a 0 for x sub 3 in that last position. So x sub 3 is equal to t. So x sub 3 is t. X sub 1 is 13/2 times t, and x sub 2 is -2t. So p sub 2 is, let's get the order, 13/2, and then I get -2 and 1. And if you jump over and look at what he has, see, he has it, looks like it's kind of flipped, and then he has that -7. I pick up a 7 for the next eigenvector. But again, linear algebra is a really cool class of equivalence, and so what we're getting is still equivalent. It doesn't look pretty. Let's just use blue. Okay, so for lambda equal to 1, you recall that the matrix that we got was -1, 0, 0, 2, -2, 1, -9, 2, and -1. And then that's reduced on your calculator to 1, 0, 0, 0, 1, 0. See how I get the 7 over there? So this implies that you should be able to look at it and tell what the eigenvector is. Let's see. Let's see if you get it. So here this is going to be -7. This is going to be 1. It's going to be 1. You know, it's times the t. Um, so the matrix P that you want consists of these eigenvectors in that order. Now, is the order unique? No, it's not. I'll just write my order based on how I found the eigen values. Um, the way it's listed in the for the solution in web assign, he didn't use the order of the way I'm getting my eigenvalues. So I think he probably picked 1 or 4 first or something like that. But it doesn't matter. Um, the 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 main solution is indeed unique. So my first, so I better write that in black. Let's go back to black. So P is equal to 1, 0, 0, and then P sub 2 is 13 over 2, -2 and 1, and then this is -7, 1 and 1. Okay, and now with that, what we want to do is to so if you go back, so that would be P. I'm going to put my values of P that I found, and you do that. You know, as you work with your calculator and you get your results, you if you do it the way I'm showing you, you put your results in there. It's going to mark it right. Right. So and now when you do the P inverse times A times P, let me show you the shortcut of doing that. Just you can do it the way I did it. So here P inverse times A times P. I just wrote in I put this in the calculator. I put P in there. So that's that 1, 0, 0, and then 13 over 2, -2, 1, -7, 1 and 1 times, then I said times the matrix A. I put the matrix A in the graphing calculator. Oh, that's the inverse. In the graphing calculator, I just typed in this matrix and then I said raised to the power. Once I closed it up, closed the bracket, raised to the power of -1. Then times A. It's going to be fascinating what you get once you hit enter. If you don't have a syntax, right? I guess that'll be fascinating too. And then times the matrix P. So what this guy gives you, so what I'm saying is I never solved for P inverse. I just said I put the matrix P and just raised it to the power, then times the matrix A, then times the matrix P. And here's what my calculator gave me: 2, 0, 0, 0400001. Look at the main diagonal. Aren't those the values, the eigenvalues in the order that I listed them? 2, 4, and 1. See that? 2, 4, and 1. See, he listed his. He had the 1 and then the 2 and then the 4 last. Doesn't matter about the order. Okay. Well, I thought that was pretty cool. Hopefully you like it. Let me know.